created a small review of the entropy. So here we have the formula that we are going to use in today's lecture. So that to find the entropy change of pure substances. So when I say that entropy change, it is very similar to when you say that temperature change. It is to make the review easier. So when you say the temperature change, for example, T2 minus T1, okay, you have some formula to find T2 minus T1, or if you have the pressure change, so that for that pressure change, you have also the P2 minus P1, okay. So for each of it, if you are trying to find this one, you have the formula for that one, and you are using the formula to find the temperature change. Or if you are interested in the pressure change, also you have the formula for the pressure change, and you are finding it. For example, if it is an ideal gas, you can use the ideal gas relations. If you have the flow inside the pipeline system, you have the formula for the pressure change in that pipeline system. Okay, so that similarly here we have the entropy change of the pure substances. This one is very important. And here S2 minus S1, entropy change. We have two groups of the pure substances. We have the incompressible substances with the constant specific heat, if the specific heat is constant, and also the variable specific heat. Constant specific heat means that this is an assumption, and we are saying that Cp and Cv. So this is an assumption. This can be true or not. They are not dependent on temperature. Okay, this is the first case. So we are assuming that the Cp and the Cv do not change with temperature. Okay. But this one is the variable case, which is the real one. This one is the real. Okay, this one is the approximate or assumption. For the constant specific heats, if you are trying to find the entropy change, you are using this formula. Okay, C average ln T2 by T1, if it is incompressible substance. But if if it is isentropic case, isentropic means if you have the different, for example, if you have the isothermal case, in that case you have the T2 same as T1. Or if you have the isochoric case, you have the V2 is equal to V1. The volume doesn't change. Similarly, we have the isentropic case. In that isentropic case, the entropy doesn't change. Entropy remains constant. Okay. And for that one, for the incompressible substances, if the temperature is constant, then you have the entropy constant. Entropy doesn't increase or decrease. So if you are using the real one, which is the variable specific heat, for this one, you need to look at the tables. Okay, you have the tables. So at the end of the book, so if you remember the tables that are at the end of the book, for that tables, there is also the line where you are including the entropy of the pure substances. Now I will show you one example here. So let me share that screen for you. So you can see that. So now you will see the entropy column. So here you have the entropy. So specific volume part, it is from you have used from the first thermodynamic class, and the internal energy, and the enthalpy, it is also, we have used it for most of the time. And now we are going to use, we will use entropy part, which is the saturated liquid SF, evaporated. So the SF, S2 minus SF, you can say. So, and at the last part, we have the saturated vapor, so SG and SF, and the difference between which is given as SFG. Okay, so this one is the entropy change during evaporation or boiling or the condensation. Okay, now I'm going back to our slide. So that we can continue. For the variable one, I've said it, we are using the tables. So next is the constant specific heat. for the ideal gases. Okay, now we are finding entropy change of the ideal gases. For the ideal gases, similarly, we say that this is assumption. Okay, this is also as an assumption. Okay, we are saying that a Cp and the Cv is not dependent on temperature. Okay, again, Cp, this is not true. Okay, this is not a function of temperature, and this is not a true case because Cp and the Cv is a function of temperature. But it is an assumption. And if you have the entropy change for this case, you are using this formula. You have two formulas. You can use this one or that one. Similarly, if the entropy is constant, S2 is same as S1. It doesn't change. You can use this one or that one or this one. Okay, you have the different three formula. And if you use the variable specific, heat, then in that case, you will have the entropy change, which is determined by this formula. And these are these values, this value. You will need to look at the table. From the table, you will find, you see it is written here, the tables. But you also have the formula here. And if it is the isentropic case, in that case, you can use this formula, or you can use that formula, or you can use this formula. In all of these cases, you see some unknown variables, for example, PR2, you see new R2, new R1, etc. So these are the variables that you should look or refer to the table. Okay. Similarly here, this one is also table, this one is also table. You can see it is tables. Okay. Now with this one, I'm moving on the next slide. This is just a review, okay, review to understand the problems easily. And we have the non-conservation of the entropy. If you remember from the previous classes, you have the conservation of energy, you have the conservation of the mass, conservation of momentum. For the entropy case, it is a non-conserved property. So non-conserved property means that entropy can be generated. Okay, this one is very important. It can't be destroyed, but add it. It can't be destroyed, but it can be generated. Okay. It can't be destroyed, but it can be generated. This is the essence of the entropy. So I have a system here. So this is an open system, and there is some flow. So let's say it is fluid that comes into the system, and the fluid leaves the system. Okay. And this is my control volume. This is the control volume, and the fluid enters to the system. Fluid leaves to the system, you can see it at the outlet, you have the fluid. Now what I will do is that I will write the conservation of energy and the conservation of mass, non-conservation of entropy for this system here. So we have this amount of work transfer out of the system. You have this amount of Q dot out, this one is also out of the system. You have the Q dot in, you have work dot in, and you have some mass flow rate into the system. You have mass flow rate out of the system. This is some fluid here. Okay, so here you have also the fluid. If you write the conservation of energy, which is this one, for the conservation of energy, change of, this can be, so first let me add it, this can be turbine, compressor, or any other system that is open. Okay. So if you are trying to write the conservation of energy, change of the total energy of the system, so that the system has total energy, which is the internal energy, kinetic energy, and the potential energy. Okay. Change of it, of the energy of the system, the total sum. So this one will be equal to mass flow rate multiplied with this U plus P by rho. This is also called the enthalpy. This combination is also called enthalpy. Mass flow rate multiplied with enthalpy, with kinetic energy and with the potential energy, plus the heat transfer and the work transfer. These are the in quantities into the system. You can see here we have the in, here you have the in quantity, and the minus, similarly here you have the mass flow rate, and this quantity is also enthalpy, H, and the next one is kinetic energy and the potential energy. This one is for the mass flow rate, and you have also the work and the heat transfer out of the system. This is for the conservation of energy. Now what I'm going to do is that I will write the conservation of non-conservation actually. This one is, let's say this one is the balance. Instead of conservation, this one is the balance of entropy. Now you can feel the difference. Here you have the conservation because you have some constant amount of energy. This energy cannot be increased or decreased. It only changes form from one type to another. But here the entropy is not conserved property because it can be generated. During the process, you will have entropy generation. So for the entropy balance, you will have the change of entropy, very similar to here, change of total energy. Here you have the change of entropy. So S, entropy of the system. Change of entropy will be equal to the mass flow rate multiplied with the entropy into the system. So into that system, you will have the, instead of kinetic potential and the enthalpy, you are carrying entropy into the system. Okay. Plus that the heat transfer into the system, plus heat transfer into the system, and divided by the boundary. This one is the boundary temperature. So boundary temperature, that the heat is transferred. You can see that the boundary temperature TB is shown here. So the system has some boundary temperature here, but for the heat transfer, we are interested in the boundary temperature here. So let's say that TB in. Okay. You can see now that this is the for the inlet. For the outlet, you will have the mass flow rate multiplied with the entropy that leaves the system, similarly to energy balance. Okay, and the plus Q dot where it leaves the system, and where it leaves, here you will have also the T boundary out, okay, the temperature that it leaves, and this addition, this one minus that one, plus the generation part, entropy generation. This is the part that we add to the system because during that balance process, you will have the entropy generated inside the system. So here you will have the generation of entropy. So when you say generation, it is not so easily understood, but let's say that creation of entropy. Now you can see what's going on. Okay. It is something like a production facility. During that production facility, you have the entropy transfer, you have the heat transfer, but inside that transfer, you have the creation of entropy. Additional entropy is created, and that is what creates a problem for the solution of the questions. And here you can see the difference now. The work, let me add it, work can't. So the heat, you can see heat can transfer entropy, but work can't transfer entropy. Okay. Work can't transfer entropy. In other words, it means that it is a difference between the work and the heat. So heat adds entropy to the system, but the work can't transfer entropy. It cannot add entropy. So it cannot add or let's say that remove. Okay, that is the difference between work and the heat. Okay, with this review, now I can start to solve the examples. When I solve the examples, you will see that I will refer to these reviews here. Okay, most of the time, I will go back to these reviews, either this one or that one. Okay. Any of the reviews, any of the questions, you can see that we refer to this one, this slide, or that slide. Let me start with the first example. We have the 2 liters of milk at 33 degrees Celsius, and it has been cooled down to the constant temperature of 8 degrees Celsius. Okay, so we have the milk. So it has the T1, which is 32 degrees Celsius, and the T2, which is 8 degrees Celsius. And it says that treat milk same as water, because you know them that most part of the milk is water, therefore it's not a problem that we can treat this one as water, because it carries the similar density with water, which is about 1,000. It carries the same CPCV with the water, it is about 4. So therefore it's not a problem to treat milk. You can even treat the vegetables and the fruits same as water, because they carry the same property as water, because they have most of the parts of the fluid, and the vegetables are water. Therefore, no problem if you treat them as water. Okay, now let's solve it. So in this case, we are interested in entropy change of pure substance, and this pure substance is incompressible. You see, pure substance incompressible. Now I'm going to the first slide. I'm interested in entropy change of pure substances and the incompressible one. So now comes the approximation. If I say that the CP/CV of the incompressible substance is constant, I will use this formula. But if I say that it is not constant, if it is variable, then I should go to the table. So you can see the difference now. So I will say that the CP/CV is CP and the CV, it's not function of temperature. It doesn't change. So it means that if you have the CP chart or CV chart versus temperature, you will have something like this one. But in the real case, it is not. It can decrease or increase in that manner. Okay, therefore, no problem for our case. The temperature, you can see the temperature difference, delta T is small. Since delta T is small, we can say that CP and the CV are constant. Okay. So if you take the small delta T here, you can see the change is very small, and therefore we can assume that CP and the CV are constants. Now I will just use the formula that is given here. So the formula says that C average ln T2 minus T1. So that S2 minus S1 entropy change will be equal to C average ln T2 by T1. Okay. Now if you look at the units here, let's look at the units and then solve it. So this one has a same unit, therefore there is no unit here, no dimension, no unit. So we have cancelled out the, actually this one is dimension. Let's play with units. Okay. So C average, this one has a unit of joules per kilograms, degrees Celsius or Kelvin, it doesn't matter. Let's say Kelvin in this case. So that this one has a unit of joules per kilogram Kelvin or kilojoules per kilogram Kelvin, it doesn't matter. And you can see that now the S2 minus S1 here will have the unit of joules by kilogram Kelvin, the difference of entropy. But if I multiply with this one, with the mass, I multiply with m, so I will also multiply this part with m, and then you will have joules by Kelvin. That is the difference. So you can now see the difference here. In this, all of these formulas, entropy change, S2 minus S1 is per unit mass. Okay. If you have the mass, we will add it. Okay, let's solve it without losing time. So that C average, I will take the C average as water. It will have the, this one is the water C average, and the kilogram Kelvin, and the ln. So here, for the T2 by T1, you cannot use degrees Celsius. Okay, you can't use degrees Celsius because the reason is that this is division. For the division, so that Kelvin and the degrees Celsius matter. So therefore, I should convert it into a SI unit, so the thermodynamic unit or SI unit, which is the Kelvin. So it will be divided by 32 plus this one. Okay, and if you do this calculation, you will get the entropy change of the milk. So let me write the final value without losing time. If you have the value, you can say it, no problem. So that the final result is negative. Final result is negative 0.34. That is negative 0.34. So times 10 to the power of 3 joules by kilogram Kelvin. Okay, that is the final result. Or you can write it as -340 joules by kilogram Kelvin. You can see that entropy of the milk has decreased. So this one is not a problem. The entropy of the milk has decreased. So you can, if you think of this one as a system, let's say that this one is the milk, and these are the surroundings. Okay, so let me add this one. The milk and the surroundings. So the entropy of the milk can decrease. So for example, if delta S milk is less than 0, it means that the delta S total should be greater than 0. But this one is always. Okay. Total entropy of the system, so milk plus the surroundings, cannot decrease. It will always increase, or at the minimum case, it will be equal to 0. That is, happens in ideal conditions. And in real conditions, one of the subcomponents of the system may have the entropy decrease. For example, in this case, the milk has the less entropy. It has decreased. But the total entropy, which is the entropy of the milk, so this one is entropy of the milk, plus the entropy change of surroundings. This total entropy change, it cannot be less than 0. It should be equal or greater than 0 due to the third law and the second law. Add this one. Second law, thermodynamics. And this third law also puts some limit. Okay, so that this is the result.
Sir.
Now, I found the entropy change of the milk, which is about this one. Now I will find with the mass here. So this one is per unit mass. So if you multiply m s2 minus s1, so you can write this one as with the uppercase letter. It will be that 2 kilograms multiplied with -340. So this one joules per kilogram Kelvin. And this one will be equal to joule by Kelvin, and it makes -680. Okay, this is the final result. So we have found it. The entropy change of the milk is -680 joules per Kelvin. Okay, so
can I ask a question?
Now, with this one, I can move on to the next example, but it seems that somebody is asking a question. Yes, somebody is asking a question. Yes, my friend,
yes.
Go on.
Sure. In the first case, we found specific entropy change.
Yes, specific entropy change.
Okay, thanks.
Okay, thank you. Okay, so I have finished the first example. You see that whenever I solve the example, so for today, you will either use this equation here or this equation. Okay. No need to worry about the theory. And now comes the second example. We have the aluminum radiator of 6 kilogram, which holds 1.5 kilogram of liquid. So we have a radiator here. This one is made up of aluminum radiator, and it has a mass of 6 kilograms. And inside of this one, you have the R, so 134A, and this one has a mass of 1.5 kilograms. And it is at -9 degrees Celsius. Okay. So then the unit is heated to some temperature with input of 220 kilojoules. Okay. Heated means that, you know it from the first thermodynamics, you will have the heat addition, which is 220 kilojoules. And to find the final temperature as well as the entropy change of total mass. So we have to find the final temperature and the entropy change of total mass. Assume both are always in thermal equilibrium. This one is very important. So we have the thermal equilibrium at the beginning of the process, at the end of the process, and at each stage of the process. Okay, so it means that the initial temperature T1 of aluminum is same as the T1 of the refrigerant, which is -9 degrees Celsius. And the T2 of aluminum and the T2 of refrigerant, so that R is a, so there is a problem here. So T2 of refrigerant, we have the R134A, but this one is unknown.
So
Okay.
correct question.
So then what I will do is that this one is T1 and this one is the T2. So I'm going to find the temperature, final temperature, as well as the entropy change. So someone is asking questions, so let me, yes, Fikrat.
Is it possible thermal equilibrium in reality?
No, it is not possible. It is just for to make the things easier. Okay, it is not in real time. You cannot have the equilibrium at each stage. Okay, it is only for the simplification.
Okay, thank you.
Okay, so that we have it. We have this one. Good. Now, first we will find the final temperature and then the entropy change. So that, but one thing I have forgotten to add here is that this one is the first law of thermodynamics. This one is first law, and this one is second law. This one is second law. This one is second law of thermodynamics, balance of entropy. This one is the first law. Now, to find the final temperature, I will just use the first law, and to find T2, I will just use the first law here, and the first law says that we will have the change of internal energy. So let me go back to the previous slide here. Change of internal energy, kinetic energy, and the potential energy of the system will be equal to these equations. But in most of the problems, kinetic energy and the potential energy are small, and therefore they are approximately on the order of 0. Okay, we don't consider it. If we go back to here, so therefore I will just write the internal energy of the system, change of it, will be equal to that in minus out. And the change of the internal energy of the system, this one, to find it, I will first select my system here. My system will include, this one will include the radiator and the aluminum and the refrigerant. So it will be, so that del U total, and that will be equal to delta U total, and that one will be equal to that U2 aluminum plus the U2 refrigerant, so minus U1 aluminum and the U1 refrigerant. U2 aluminum and the refrigerant plus, it is the second stage minus the first stage. And for inlet properties, we don't have any outlet. This one is 0 because this one is closed system. Okay. And we don't have inlet except the Q. So Q is 220 kilojoules. Now let's find it. So I can arrange this equation here. So I can write this one as U2 minus U1 for the aluminum plus, so that U2 minus U1 refrigerant. And that one will be equal to 220 kilojoules. And for the aluminum, I will just use MCV delta T, which you know from the high school. This one will be equal to MC delta T. And for the refrigerant, again, I will just use MC delta T. Okay. And the mass of aluminum is given, which is 6 kilograms. And the delta T, it is unknown for the second stage. Therefore, T2 minus T1. T1 is -9, therefore it will be T2 plus 9. And the C value for the aluminum, which is that 0.9. This is from table, okay? I've taken it before, so I'm just writing the value here. 0.9 kilojoules per kilogram degree Celsius. This is for the aluminum. Now for the refrigerant, I will do the similar calculation. Mass is 1.5 kilograms, and the C value for the refrigerant, again, I've taken it from the table, so 1.35 kilojoules per kilogram degree Celsius. And the delta T here, again, it will be T2 plus 9 degrees Celsius. So you see, there is only one unknown here, and all of the variables are known. Okay, I know the T1, I know the C value, everything is known, only T2 value. Okay, so you can take the T2 plus 9 out of the brackets and solve the rest of it. So I will tell you the final answer here. So let me tell you the final answer. So it will be 20.64 degrees Celsius. Okay, so if you add here we are adding heat, therefore the temperature increases. Okay. This is the first law. I've used the first law and find the temperature, final temperature. Okay, so this one is just MC delta T, which is equal to Q added, but I've done it in detailed version so you can see what's going on here. Okay, so if you have questions till this part, you can ask. Otherwise, I am moving to the second part of the question where I will try to find the entropy change of the pure substances. If you have questions, you can ask. It seems that no question. Okay, so I'm continuing to the second part, which says that find the entropy change of the total mass. Now I will do the same step as the first law. So let me show everything one more time here. With the first law, I will write the second law for the system. So the final temperature was 20.64 degrees Celsius. Okay. This is from the first law. This was from the first law. Okay, I've done it. Now I'm doing the same process for the application of the second law. So this is the radiator, if you remember it, and it has the aluminum material, which is 6 kilograms, and inside of it you have the R10348. So now I'm selecting the same control volume here. Now I will apply the second law. Okay, to apply the second law, if you remember the first law, what it says is that change of the energy of the system is equal to in minus out. This is the first law. And for the second law, the process is very similar. You have the change of entropy of the system. This one is the system. The change of entropy of the system is equal to the total in minus total out. Okay, this is the same. You can see the change of internal energy is in minus out plus the generation. This is the difference between the first law and the second law. This is the second law. Let me add it from somewhere here. Second law. If you go back to the formula here, you can see it is the same. So you have the change of entropy. This one is for rate, no problem. You can write in a similar manner. You can say that the del S will be equal to, so you have the mass flow rate and you have the entropy plus that Q. Now it will be not Q dot, it will be Q. So you will have the Q divided by the boundary temperature. These are the in quantities, you can see it. This is the in, minus similarly, the same quantities for the out. Let me write it so that everything is all right. So you will have the mass with the entropy and the Q by TB, and this one is the out. Okay, and then for the last case, you will have the generation. Okay. This is very similar to the first law, but in the first law you have the work as well, but in the second law, work doesn't play any role because it doesn't create entropy. Okay, it doesn't transfer entropy. That's very easy stuff. So let's apply this one to our system here, and the question says that find this part, the change of entropy of the system. You can see entropy change of the total mass. And here, our system is total mass. But you can also play with the right and the left-hand side. For the right-hand side, there is no out quantity because the Q out is 0 and there is no mass flow rate. It is closed system. Okay. So if you remember from the first law, you have the in quantities that can be by work, that can be by heat, work, and the mass for the first law. And for the second law, you have the in or out properties. They are the same. It can be by heat or it can be by mass. There is no work. Okay, that is the difference between the first law and the second law. And in our case, it is closed system, therefore there is no mass. And in odd quantities, there is no Q, therefore it is 0. Therefore, the odd part becomes 0. Generation part is always there. And now comes the inlet part. For the inlet part, you will just write the heat transfer Q in to the system. Say that you have the heat transfer at some point here. You have the heat transfer. Let me, it's one more different color. It can be at any point. It's not so important. Let's say this one is the Q in. And the Q in crosses the boundary at some temperature. That is what we are interested in, this temperature. This T boundary in. Okay. That is for the boundary temperature for Q in. But in our case, the boundary temperature changes with respect to temperature. Okay. Sorry, boundary temperature is function of time. Okay. Therefore, the right-hand side seems very difficult for us to solve it. Therefore, what I will do is that I will just solve the left-hand side, this part, which is very easy. Okay. But because the right-hand side is a function of time, the boundary temperature, that the heat is transferred. So I can write this one as the Q in divided by the boundary temperature that is transferred. Okay. Boundary. But in our case, it is function of time, therefore difficult to find. So I will find the left-hand side. So what I'm trying to say is that you can solve the right-hand side, find the left-hand side, or you can solve the left-hand side, find the right-hand side. See, they are equal. So I'm solving the left-hand side. Okay, so if I do that, then I will have it will be S2 of the aluminium plus S2 of refrigerant minus S1 of aluminium plus S1 of refrigerant. Okay, this is for the left-hand side. And I can group it again, so it will be that S2 of aluminium minus S1 of aluminium plus S2 of refrigerant minus S1 of refrigerant. Similarly, U2 minus U1. I'm doing the same stuff here. So the first one, change of entropy of aluminium. So I know that change of entropy of aluminium, entropy change of pure substances. It is aluminium pure substance. Here we have the aluminium and the refrigerant. For aluminium, it is incompressible substance, and I am assuming that the specific heat is constant, and therefore I will use the entropy change with this formula. You see? And for refrigerant, it is also isoentropic incompressible, and I am also assuming constant specific, and I will use the same formula here. I think you have understood this process, so I will write it for the aluminium. S2 aluminium minus S1 aluminium, it will be equal to M mass C average ln T2 by T1. Okay, the mass of aluminium is 6 kilograms multiplied with the C average of the aluminium. So let me look at it again. So is 0.9, yes, 0.9 kilojoules per kilogram degree Celsius, multiplied with the ln of T2, which is 20.64 plus 273, divided by T1, which is -1 plus 273. Okay. This one will be for the aluminium. If you do that, you will get the result as 0.56 kilojoules per Kelvin. Okay. Now, similarly, for the refrigerant, I will write it S1 refrigerant. It will be that M C average ln T2 by T1. That one will be equal to the mass of it. The mass of refrigerant is 1.5 kilograms multiplied with its specific constant is 1.35 kilojoules per kilogram Kelvin, and multiplied with the same equation here, which is 20.64 plus 273 divided by -9 plus 273. And this one will be equal to 0.21 kilojoules per Kelvin. Okay, but since I'm interested in this one minus that one plus this one, so I'm interested in delta S total. Okay, and that one will be equal to 0.56 plus 0.21 and 0.77 kilojoules per Kelvin. Okay, and I have found the left-hand side, and the question has been solved. The question is asking entropy change of the total mass for the left-hand side. Okay, it doesn't ask about the generation of entropy. So it doesn't ask what is the generation of entropy. It could ask, but it doesn't ask because the boundary temperature here is not a constant. It is function of time. Therefore, it is not so easy to find the Q in by TB in, the boundary temperature in. If you have questions, you can ask. Otherwise, I am moving on the next example. But you should always remember that we had made the approximation that, so this one is very, this assumption has been used in previous example as well as here, that Cp and the Cv are not function of temperature. Okay. Cp and the Cv are not function of temperature. Okay, so this is the second example I've solved for today. Now comes the third example. We have a handheld bicycle pump with a volume of 30 centimeters cube in fully extended form. So this is the handheld bicycle pump. And when it says that when it is fully extended, for example, the piston is somewhere here. Okay, and the volume of this portion here, the volume here, it makes the 30 centimeters to the power of 3. While holding your thumb over exit of the pump, so this one is the exit, that stopping the fluid outlet, and you press the piston in raising the inside pressure to 290 kilopascals. What you are doing is that you press your thumb over exit and press it. And when you press it, the P2 becomes 290 kilopascals. Okay. And the outside pressure is 101 kilopascal at 25 degrees. So P1 is 101 kilopascal, and so let me write this one as outside. So I will do it as P1. So P out is 101 kilopascal, and the T out environment is 25 degrees Celsius. You have two cases. In first case, the process is so quick, so you are doing it very fast, in the order of 1 second. And in the second case, it is so slow. You are doing it slowly, in the order of 1 hour. So you will not have patience for 1 hour, but let's assume that you have done it in 1 hour. Okay, then for both cases, in any of these cases, find so firstly explain what are the differences in those cases. This is the first question. And the second question is that what is the entropy, final volume, and the temperature, assuming constant specific heat for both of the processes. So it says that what is the final volume and temperature, and what are the differences in those cases. Firstly, let's explain the first case, and then we are going to the second case. If it is very fast, okay, so it means that, so there is no time for heat transfer. Okay, if it is very fast, then there is no time for heat transfer. Okay, therefore, Q will be 0. Okay, because so if you remember from the first thermodynamic class, Q needs time. Okay, the heat transfer needs time. Okay, but work doesn't need. Okay, work transfer, it doesn't need time. Okay, but the heat transfer needs time. Therefore, that is the reason that heat exchangers are large. Okay, that is the reason that we have large heat exchangers, or we have the fins. Okay, we have the fins, or we have the large heat exchangers, because the heat transfer needs time. Okay, and to decrease time, so to decrease time effect, what you are doing is that you are increasing area, surface area. So to decrease the time effect, you are increasing the surface area. That is the reason that the queue needs time. So similarly here, if the process is very fast, then there is not enough time for the heat transfer, and the queue becomes 0. Okay, and if the process is very slow, and for the slow process, very slow process, okay, in that very slow process, what will happen is that, so that there will be time for heat transfer, so will be enough time, actually, enough time for heat transfer. But the main difference from the first one and that one will be that since there is enough time for the heat transfer, the pump will be in thermal equilibrium with environment. Okay, so that pump will be in thermal equilibrium with the environment, because there is enough time for the heat transfer. At each stage, you will have the thermal equilibrium with the environment. And let me give this second one one more. Say that this one is the pump here, okay, and you are pressing the pump. Okay, you are pressing it with the piston here. You have the piston, and you are pressing it, and the temperature rises to, for example, 25.2 degrees Celsius, and the environment 20 degrees Celsius. And since you have the enough time, because the process is very slow, you have the heat transfer, and this one drops to 25 again. Okay, and you press it again, this one rises, for example, that 25.2 again, and therefore heat transfer, and therefore 25 degrees Celsius, and the temperature drops to 25 degrees Celsius again. Okay, you see, the process is very slow, and therefore due to slow amount of the process, and you have the time for each stage for heat transfer, and you have the thermal equilibrium with the environment and the inside of the pump. So with this one, I'm stopping here. So I will take the attendance.